Hello everyone, my name is Jack Sifri and I will be talking about design methodology for RF modules and design challenges that RF modules face and how to conquer them, how to deal with them. So the agenda here I have is basic building blocks of RF module, and then I'll go through the design process, how to deal with these design challenges. This is a picture just to kind of illustrate what I'll be talking about when I say RF module. If you look at the left, you will see some kind of laminate board that has multi-layers, 2-4 layers, and it consists of IC chips sitting on top of it. That is like a power amplifier, digital control switches, there is bond wires, solder bumps, SMT components. All these constitute in making the RF module that I'll be talking about. So the first thing, when you have a whole RF module is that the heart of the RF module is really the IC chip. The IC chip has, the IC design has to be robust. It has to be very well designed. Otherwise, you're going to run into serious problems when you integrate everything together. So when I say about this, notice here, if you're designing the IC, whether it's a power amp or a switch or a LNA, Q factor reduction for robustness, the Q factor reduction is very important. The matching network topology has to be very insensitive to the variation around it. Broadband network, all these are very important in designing the IC to start with. So you can apply, a lot of statistical tools to help you achieve this. And last year I gave a microapp paper specifically on this topic, how to make your existing design more robust. And I put this slide here just to remind you, take a look at it last year, and it has a full description of how to go about designing the IC itself, being insensitive. But just to illustrate to you the concept, I give a simple example here of a low noise amplifier that has a matching network here. In fact, I list here 3 different matching networks. And I'm applying the last one here, the third one, series line, open stub. Here's the series line, and here's the open stub topology. And this low noise amplifier has to be 0.7, less than 1 dB noise figure. When we built it and we tested it in the lab, the noise figure was 8 dB. It's like it's a noise source, not an LNA. So we try to investigate the problem, and notice all these matching networks here that I talk about. We plotted the impedance of them versus the optimum noise figure for the FET, for the transistor. Notice that these matching networks, different matching networks, the impedance goes far away from the red area. Whereas later on we discovered a very simple matching network, which is a single line, high impedance, and notice its impedance just lie right on top of the red area. This is a good design, and it's much simpler too. In fact, looking at it this way, notice that the single line noise figure is broadband and it is low noise with frequency, whereas the others change really fast and it goes really high noise figure, very sensitive. So just to illustrate to you, it's an IC design. Just make sure that it is designed properly and it's not sensitive to the variation. Now, you designed your IC and you have a really successful topology and you succeeded with that. The next challenge you have is the proximity effects. You go ahead and take your design and you simulate it using EM simulator, and you find out that your frequency shifted or your gain is lower or some mismatch due to coupling effect and proximity effects of various components in the design. And this one here, this design, which is a KU band down converter, it's really quarter the size. They try today to dense everything together into a very small area. So just imagine if this is really dense, it's even the coupling is going to cause more problems, in your design. So just to illustrate this concept, I go back to the basic inductor theory. And if you have like spiral inductors, 3 of them in series, notice the dot here, this one is flipped. You flip it. And when you flip the dot, the current flow is different in every inductor. The mutual inductance between each one could be positive or could be negative. So one would think that the total inductance here is 9 plus 6 plus 3, which is 18 nanohenry. But in actuality, it's 15 nanohenry when you include the mutual inductance based on the dot and the current flow. So this is very important when you design IC with spiral inductors in your design. To illustrate this, I put a case study. I put a spiral inductor here. Notice the current goes through the green. It goes through the green, so they are in the same dot going in. The mutual inductance is kind of low because they are far apart, the 2 spirals. Notice the inductance is the black curve. Now, what I did here, I put the current going through the green, the layer, and then here it enters the red layer. So I flipped that spiral and still has the mutual inductance far. Notice the mutual inductance reduced that inductance value, the red curve. Then I got them really close together, and the mutual inductance is very high, and it's negative, it subtracts, so it went down to 7 nanohenry. But this is just the beginning of the story. This one I showed you in the previous slide, it's red. Now I take this structure and I flip it vertically. It's the same identical structure, but I put it vertically instead of horizontally, and I get the green results. Why? It's just like the nature of the field and the current orientation, I get the green result. And in this case, the blue I showed in the last slide, I just flip it and I do it this configuration vertically, and I get 6.5 nanohenry. The difference between the red and the purple is like 10 to 12% different, 12% difference. We're not even putting statistics yet, like the width of the line changing or this. So this is a big effect, and it's going to affect your design, when you don't consider this. So you can see why I'm talking about this, because in IC design you have such configuration, vertical or horizontal, and all this coupling in this. Then I said, okay, let me take this structure, horizontal and vertical, and let me build a circuit, simple circuit, a filter. So you can see this is a low-pass filter using the horizontal topology, and this is a vertical filter using, the vertical topology, the same exact dimensions, spacing, everything. And I plot the results doing EM simulation. Notice at the results, the red versus the blue. Big difference in the results, the same exact dimensions, but the the orientation was different, here. If you're looking at a rejection at 7 gigahertz, 50 dB rejection here, forget it if you use this topology. You're going to be in trouble. Whereas if you use this topology, you will get it. And look at the bandwidth also is different. So be aware of this kind of things. That's where you run into problems when you kind of don't know where the problem is coming from. Be aware of the spiral coupling and the orientation and all this in the layout. Here's a practical example. It's an LTE power amplifier. Notice that I have this vertical topology right here at the input. And when I did the simulation using the Circut model, it's right here, the input return loss. When I did EM planar simulation, it shifted, indicating that there is some kind of a negative mutual inductance, and the inductance was smaller, resulting in a shift in higher frequency here. But the bottom line is be aware of this. It shows really the shift here. Now, you do have a design like this, and you find out that the frequency shifted. What do? My idea, my recommendation is go to the Circuit model, do some tuning on some components really fast, find out which components affect the frequency, because you want to bring the frequency back. Once you find those components, let's say 3 components really affect the frequency, you can parameterize them, these components, And you can run optimization using momentum or EM optimization. So it optimizes and run EM simulation at the same time and really try to fix your design. And this is an example where the dashed line was the beginning and then the solid line where it was fixed after 7 runs of EM optimization. Now the next step is you take that IC and you want to package it. You want to put bond wires, you want to put laminate, package, all this. So you have a new type of design challenges that you have to encounter. The bond wire effects, the substrate loss, the substrate coupling, all these effects here. I did simulation on 4 cases of that LTEPA. Notice I shared the results here before. Case number 3, I took that MMIC momentum simulation and I combined it with the package FEM, 3D FEM simulation. And in case number 4, I simulated the whole structure using FEM simulation. Notice the effect. I showed you these results before. Notice now the frequency is cut shorter because the bond wires, which created some frequency shift here, and we got introduced some losses, mismatch losses and substrate coupling losses. And notice the whole amplifier even have more loss and it has different characteristic than combining the 2 separately. So be aware of this. Do EM optimization to fix the design back. But let's say you have the chip already manufactured and you are in the lab testing it and you get something like this. What do? You don't want to go and spend a lot of money to refabricate that chip. You want to fix it as a chip itself. So some people, what they do is to use an external matching on the laminate board. Notice here I put 2 bond wires to reduce the effect of the inductance. This is, by the way, a different amplifier example. And notice at the laminate, I put a matching network. So you can see the dotted line is the initial results. And after I matched it and I put double bond wires, notice that I shifted it to the right, so I got the better results. This way I don't have to go back and design it and refabricate it or something. It's another methodology. Next, I want to show you more design challenges that you would encounter when you put the IC and a package. So I constructed something very simple just to illustrate the concept. Here I have an inductor IC sitting on a package, and this is the ground for the IC, and this is the ground of the laminate, the package. I have 2 different grounds. It depends where I define my ground. So I wanted to simulate this. First, I simulated 1 inductor. Then I put 2 inductors not connected together just to kind of see the effects of the mutual inductance here. And then I got them closer. Notice this case and this case have the same inductance, the blue and the purple, or here, because the coupling is really far. So this is really identical to this. But when you get them really close together, even though they are not connected, notice the double humps that I get in the inductance. So if you're working at 7 gigahertz or in this region, you are in trouble. You get all kinds of variation in the inductance, and your circuit will start acting up and showing different results. Now these double humps, I wanted to understand what is causing them. So what I did, I modeled this inductor. I made a model and I did some simulation of this structure, and I found out, but I don't have time to really show it in this, but I found out basically this double hump comes from capacitive coupling. It is the capacitive coupling between the 2 inductors and the capacitive coupling in the substrate. Those 2, when I vary them, I get the double humps. Easily it shows up. It's not an inductive coupling. It is a capacitive coupling mainly. So there is a lot of capacitance, and I have the results on my computer, but it just takes too longer to show. Then I took that structure and I said, okay, let me simulate this with the ground being the IC ground. Then I changed the ground to the package ground under the laminate. I changed my ground reference point. And notice that I get different results, blue and red. Inductance, and here's the blue and the red. Why? Because the laminate has capacitance. The laminate board has capacitance, and it added more capacitance and shifted my inductance curve. Then I put a bond wire to this pad, and I put my port right here. So you can see I got the green curve because the bond wire has extra inductance. And the capacitance, the extra added capacitance, comes from the pad, which has a laminate underneath it. It has capacitance. So there is a capacitive effect here. And then I put my input port right at the edge, and I get this black curve. So be aware of all these. Basically, I show you this. Then the next study I did, I put a bond wire across the inductor. Just above the inductor, I put a bond wire, and I simulated. And notice that it has an effect. The inductance changes. Why is this important, the bond wire on top of the spiral inductor? Because in real module design, like here's a module, notice this bond wire right here. That bond wire is sitting right on top of RF lines. And if you're not aware of this bond wire affecting sensitive RF lines, it could lead you to problem. So I shared with you all these design challenges. Please, if you have a question, see me, because I have a lot more information on this I can answer. But I wanted to share this study with you to help you. Thank you very much.